So part C asks you, at what time is the number of fish in the lake the greatest? Doesn't say find the absolute maximum value, but it does give you a closed interval, and that really speaks candidates test to me. I would say, oh, they're looking for candidates test here. So first of all, we need a function, right? We're trying to find a function. We're trying to find a maximum, so we need a function. So the amount of fish in the lake at any given time, and I used A in part A, so maybe I should call it F just so it has a different name, F for fish. So the amount of fish that are in the lake at a given time are going to be whatever the initial amount of fish is, and they didn't tell us what it was, but it doesn't really matter. I'm going to give it a letter. I'm going to say let F sub 0 be the initial amount of fish. It's really nice to your reader to, if you're going to use something, to define it like that so that they can make sense of your work. So that's going to be my initial amount of fish, plus I have some fish that are getting added to my environment. So that's going to be the integral from 0 to t of my e function. I'm going to call that e of x now so that I don't have the same variable there. So those ones are getting added. Oops, that's dx. And then I also have some fish that are removed from the lake. So those fish are going to be subtracted. So this is a function that gives me the number of fish in the lake. I want to know the greatest number of fish in the lake. So I'm going to look at candidates. So one candidate would be at t equals 0, and another candidate would be at t equals 8. And then any other candidate is going to be when f prime is equal to 0 or undefined. So if I take f prime, I don't care what the initial value is, the derivative of that's going to be 0. Take the derivative of an integral. Oh, look, it's the first part of the fundamental theorem of calculus. That's so exciting. So it's going to be e of t minus, oh, I didn't change those to x's. Minus L of t. So it turns out that the critical points are going to happen when the rate in is equal to the rate out. So now I need Desmos to tell me when are those two things equal on the interval from 0 to 8. So I'm going to go ahead and go to Desmos. Oh, so many tabs. So I'm going to get rid of this guy. I don't care about that anymore. If I look at my graph, one of the things I like about Desmos is I could just click on that and it says 6.204. That's a critical point. So I'm going to write that down. T equals 6.204. You don't need to tell anybody that you used a grapher at this point. You can just write this down and you can write that down and you're done. I would be clear about where that number comes from for your reader, but I wouldn't mention the calculator as you're doing that. You can also find that on a graphing calculator. I'm not saying you have to use Desmos, but it's kind of nice to do so. So if I plug in 0, I get just that, whatever that initial amount of fish is. If I plug in 6.204, I'm going to grab my thingamajigger here and do the integral from 0 to 6.204 of e of, oops. Doesn't like it. And the reason it doesn't like it is because Desmos likes parentheses where they belong. We want that whole quantity to be subtracted before we multiply by dt. Okay, so that's going to be 135 more fish than what you had in the initial, at the initial point. So this is going to be f of 0 plus 135 fish. Okay, now I'm going to look at t equals 8. So easy to change this to an 8. And that is going to be 81 more fish than you had in the initial. So the greatest number of fish is in the lake at 6.0204. And the justification is this candidates test work that you did. If you use the candidates test in this way, you don't need to say anything else about your justification. This is a very good justification.